Hello, my name is Benjamin Kinney, and this is a holographic success, an experiment in the principles of holography using a single exposure setup. So the purpose of this experiment was to effectively simulate a 3D object using a transmission hologram setup by creating an interference pattern in media that allows for the reconstruction of the original image, and to compare the light intensity and dimensional profiles of the hologram and the object that we chose to determine if they are accurately aligned. So first, I'm going to go through the principles of holography. So what is a hologram? Well, a hologram is a recreated three-dimensional image that preserves the likeness of the original object or subject, and it's not unlike a photograph. What distinguishes, however, a photograph from a hologram is that holograms preserve the three-dimensional data. So it's better thought of as an image of the object from different perspectives being preserved, and rather than a two-dimensional image. How does a hologram work? Well, we chose to use the setup for a transmission hologram, and how this works is a coherent light beam is split. One beam hits an object, and this object beam will go and hit a photographic plate. The other beam goes straight to the photographic plate, and this other beam is called a reference beam. And at the photographic plate, these beams will interfere, and the light will pass through the treated media like normal, however, will not transmit portions of the media that recorded interference. So the light reflected from the object creates an interference pattern that recreates the details of the object. And this is how you get the virtual image here on the bottom right. So the experimental setup that we used, well, first we sent our laser through an optical filter. The laser was sent through a converging lens here, and a pinhole was placed at the focal length of the lens so that the light would pass directly through the pinhole. And this is done to clean the beam, which creates a much clearer Gaussian distribution than before. As seen on this diagram, you can see the beam intensity distribution here has these small fluctuations, but after being cleaned, it has a much more precise Gaussian profile. Obviously, it's not perfect, but in our case, we did as good as we could. Next, the beam passes through a Gaussian beam expander, seen here. Really, this is just two lenses, and they're aligned so that the lens to the right is at, basically they're aligned so that both focal points are in the same spot. And this is done to make the beam large enough to encompass our object, as well as to collimate the beam so that the light is parallel, and this allows for better interference. We actually did a really good job with collimating our beam because it grew less than 0.5 millimeters larger in diameter at over 2 meters away from the origin, which is really exciting for us, and it actually helped us to create such a good interference pattern, as you'll see later. So the single exposure setup, as discussed earlier, is what we used in this project. And the beam was split using a mirrored beam splitter, creating an intensity ratio of 1:4 between beams. The object beam being the larger intensity. Here, the light hits the mirror, the mirrored beam splitter, and the more intense light hits this object and bounces onto our paper here, while the reference beam just hits a mirror and then bounces onto our film. Now, it should be noted that due to some unforeseen circumstances, we weren't actually able to get holographic film. So instead, our group decided to take pictures of our interference patterns to determine if this setup would be viable to create an actual 3D hologram if these materials were available. So the object that we used was a small stainless steel washer with an inner diameter of 0.5 centimeters and an outer diameter of 1.5 centimeters. That's actually a typo there. It should be 1.5 centimeters. And we chose this for its small size and low dimensionality, as well as its recognizable shape. We needed our object to fit inside of our beam, which was about 2.5 centimeters. So we had a small range of objects to choose from. And being reflective, this allowed for the most light to come off of our object. So what were our results? This is a image of our interference pattern, or our, in quotes, hologram, because it's not actually a hologram, but as you can see, it is a clear depiction of our washer. And we believe it would have etched a depiction of our object into holographic film had we had the materials and given enough saturation time. So you can see here on the right, the circular shape represents the washer. Now, what's important is that the dimensionality of this hologram matches our object. So we processed our image in ImageJ, where we split the channels and the red light was analyzed. The saturation per pixel was plotted along the X and Y axis here respectively of the image. And we use this as a proxy for the intensity of the light coming off of our interference pattern. And you can see these two major peaks in each image, roughly between 0 and 0.5 centimeters and 1 and 1.5 centimeters. And we believe that the smaller peak here is due to this reflection, as seen in this image, of our reference beam towards the camera. So in conclusion, we believe that the analysis done in ImageJ shows an interference pattern representative of a washer-shaped disk with an inner diameter of 0.5 centimeters and an outer diameter of 1.5 centimeters. And this nearly perfectly represents our original object. It shows that if in possession of holographic film, the setup would certainly be a viable setup for producing a 3D transmission hologram. And this is mainly possible due to the efficacy of our optical filter, the precision of our Gaussian beam, meaning it didn't grow as the light coming inside of our Gaussian beam was extremely parallel, and this allowed for very good interference. And of course, the alignment of our two beam paths, which were the exact same length. A few limitations of our project included that we experienced some light from extraneous interference due to imperfections on the mirrored beam splitter. There were scratches, and as well as on the lenses, led to some interference. But once we cleaned those up, it actually became much more clear. And another limitation was that the object had to be relatively simple and reflective due to the transmission hologram setup. The bouncing of light off the object is one of the major components of this setup. So it needed to be reflective as well as have low dimensionality for an easy recording. And of course, the lack of an access to holographic film or plate did hold us back a little bit in this project, but I think you can see based on our results that we were still able to create a setup that would be viable had we been given the correct materials. I just wanted to go through a couple real life applications of holography real quick before I end the presentation. Holography is used in medical imaging, actually in CT scanning and MRIs, which is, obviously extremely important for modern health. It also helps doctors display visual three-dimensional representations of anatomical structures, which helps them with diagnosing injuries and illnesses. So it's actually really important in the medical field as well as a couple other fields that we didn't discuss. Here are the citations and references. Please, if you have any questions, send me an email. I'd love for everyone to read the report, and I hope everyone has a great Christmas. Thank you.